So here I'm starting with the second part of chapter 3, atomic structure. I'm going to start with the electron arrangement or the Bohr's model. And we know that atoms have tiny positive charge nucleus, and that nucleus has a positively charged particles, and the electrons revolve around it, right? So if this is the nucleus, it has protons and neutrons, and they are surrounded by electrons which are negatively charged. So later on, the evidence started showing that electrons are not randomly distributed, but they are arranged in an order. And to understand that, let's look at some colorful chemistry. So all of us have seen fireworks, especially on 4th of July, and you see this brilliant display of colors, right? So these colors are because of certain salts of these metal ions, like strontium gives you red color, or copper gives you violet or blue, and barium has a characteristic green color. And also, if you take chemistry in future classes and you do some experiments which will involve analysis of metal ions or ions, then you will do a very common test called a flame test, which is a tool to identify an element. So basically you dip this nichrome wire in a metal ion solution, and then you put it in the flame, and they give you these different characteristic colors. So for example, sodium will give you this bright yellow color, or strontium will give you this red color, and you can identify those elements. So few more terms to understand the electron arrangement. So first we are going to look at the Bohr's model, the famous Niels Bohr. So the first term is a continuous spectrum, and all of us have seen it somewhere or the other. We see it in day-to-day life or in science class. You have seen that whenever a light passes through a prism, a white light passes through a prism, it gets split up into these characteristic rainbow colors, right? And these colors, they correspond to different wavelengths. And this type of spectra is referred to as a continuous spectrum or continuous spectra. Think of it as how the rain falls, or how the sunlight falls on the raindrops and give us a beautiful rainbow in the sky. So that's an example of a continuous spectra. And then there is something called as a line spectra, as the name suggests. You see these lines, they are characteristic of an element. So basically, when a light from a gaseous substance passes through a prism, it gives you these lines. So continuous spectrum, see how it is in continuity, right? That's why the name continuous. And these line spectra are these characteristic lines. So basically you have a wavelength here, and these are the different metals or elements which are giving you this characteristic line at a certain wavelength, and that's called as a line spectra. And this is also a very useful tool to identify elements in the labs. Moving on with this, so this is a little bit of a theory, but Niels Bohr, he worked on hydrogen atom, and he explained the hydrogen spectrum studying this electronic arrangement for hydrogen. Now, if you look at the periodic table, hydrogen is fairly simple element, right? Its atomic number is 1. So there is only one electron, and it's easier to explain the behavior of that. But when he tried to justify it for other elements, there was a need for another model. But what is this Niels Bohr's spectrum? So he explained that these electrons, they cannot have just any amount of energy. It has to be a specific amount of energy, and that energy is referred to as quantum, or when you talk it in plural terms, you say quanta. So the tiny unit of energy in a system is referred to as a quantum. And energy levels is a specific energy value for an electron. And I'll show you a diagram which will explain what I mean. So here is the energy levels on the left hand side. Okay, so you see there are the values of energy levels, which is n is equal to 1, and it keeps on increasing in this order. So n is equal to 1, n is equal to 2, 3, 4, and it can go up to infinity. And then you see how these electrons go in this direction from n is equal to 1 to higher energy levels. So this is what is meant by quantum. So this tiny unit of energy produced or absorbed when an electron makes a transition from one energy level to another. So if I have to explain you, let me explain it to you in terms of these two terms with the help of these two terms. So absorption means when an electron is absorbing this energy to jump from n is equal to 1 to any energy levels. For example, I'm making the electron jump from n is equal to 1 to 2. So that would be referred to as absorption. And then you see how some of these arrows are pointing downwards. That means they are emitting that energy when the electron is going from a higher energy level to a lower energy level. So for example, let's look here in the visible wavelength. Let's look here. This purple light or this purple line is because the electron is going from n is equal to 5 to n is equal to 2. So it is giving out or producing or emitting that amount of energy, and that's called as emission. So according to Bohr's model, the electrons can jump by absorbing an energy or by releasing an energy, which is referred to as a quantum of energy. And this is how he envisioned the nuclear atoms. So he thought that electrons are orbiting around the nucleus in the same way as the planets do around the sun. And Niels Bohr, got a Nobel Prize, and he also has an honorary element called bohrium, BH, element number 107. But as I said, it was easy to explain this model when only one electron was involved. But when more electrons are involved, what happens? So a new model will be introduced in a minute. But continuing, so according to the Bohr's model, whenever the electron is in the lowest energy state, so for example, let's recreate his model where n is equal to 1 was the lowest energy level, and then you had n is equal to 2 or n is equal to 3 and so on, right? These energy levels can go on till infinity. So this one, the lowest energy state, was referred to as the ground state. Now, if the electron is jumping from n is equal to 1 to n is equal to 2, then n is equal to 2 will be referred to as the excited state. I'm just writing short forms here. And if that electron is coming back or releasing or emitting that energy state, that energy, it is referred to as a photon or a particle of light. Okay, so that energy or that quantum of energy is referred to as a photon. I'm gonna quickly jump to this. So each energy shell has a capacity of 2n squared. So what do I mean by that? So when your n is equal to 1, you have 2 times 1 square. That means I can have a maximum of 2 electrons for n is equal to 1 shell. When I have n is equal to 4, for example, so for example n is equal to 4, I have 2 times 4 square, and that will be equal to how much? So 4 square, everyone knows, is 4 times 4, which is 16, and then 16 times 2 is 32. So whenever the shell is 4, you can have a maximum of 32 electrons, and you can calculate that for any number of n's by using this formula. So 2n square. So you can answer these two questions. What will be the maximum number of electrons in the fifth shell or the fifth energy level? So you will use the same formula, 2 times 5 square. So you can calculate, or what is the lowest energy level that can hold 18 electrons? So you know your number of electrons are 18 is equal to 2n square. So your n square will be equal to 18 divided by 2, which will be 9. And you know that 3 square is 9. So basically n square is equal to 3 square. So in this question, your n will be equal to 3. And you can cross check it by again substituting n in here. So 2 times 3 square. So again, 3 square is 9, times 2 is 12. So that means 18. So that means your answer is correct. So that's how you should know how to calculate both. So depending on that, then you can have electron arrangement. So the energy states, or n, which is also referred to as energy levels, are often called shells. So an element can have a first shell, second shell, third shell, and the electron will always go from the lowest energy to the higher energy. So for example, for hydrogen, you have 1 electron, so it will go to the first shell. For helium, there are 2 electrons. So because the first shell can have a maximum of 2 electrons, you show 2 electrons here. Now lithium, which has atomic number of 3, that means 3 electrons. So the first shell can have 2 electrons, check. What do I do with that extra electron? I move the electron to the second shell. So like that, practice for the first 20 elements. And you can always calculate how many electrons go in each shell. So here I have shown you an example, sodium, which has an atomic number of 11. And the first shell is going to have 2 electrons, right? 2 times 1 square. Second will have 2 times 2 square. So 2 square is 4 times 2, so 8. So my 8 plus 2, 10 electrons are covered for. And I know the next electron has to go to the third shell. So the limitations of Bohr's planetary model was, the main thing was, when more electrons got involved, it was not as simple as explaining the model for hydrogen where only one electron was involved, or the spectra uh, was easy to explain for one electron. So then this model was then replaced by a much sophisticated model, and that is known as the quantum theory or the quantum model. And this quantum model is based on a probability model. So you don't need to know all the details of that, but know the basic gist of it, especially for the introductory chemistry. We're not going to check on too many details, but you're just getting introduced to these models. So if anyone is interested, these probability based models were based on something called as a Schrodinger. He's the name of the scientist. He developed some mathematical equations which could locate, or which could tell you the possible location of the electron in the volume of space. So that space is referred to as orbitals in chemistry. Okay, so according to the quantum model, the three things that you need to know now, so this is, you do need to know these things. So it's composed of principal energy levels, something called as sublevels, and then orbitals. So let me explain each term to you now. The principal energy levels, sometimes also referred to as shells, they are roughly correlating to the distance of an electron from its nucleus. So think of it as a city. For example, there's a big city, right? Dallas. So that would be referred to as a shell or principal energy level. Then you go to the second term, which is sublevels, which is a certain neighborhood in that city. So each principal energy level, which is N, is divided into number of subshells, and each subshell has one or more orbitals. Okay, so there is a city which has a particular neighborhood, and that neighborhood has a house. So think of it as principal energy level, sub-level, and then where you are living is, like if you are an electron, you're living inside your home, right? So that is the orbital. So these dots here that I'm showing you in this slide are the orbitals. Okay, so the dots are telling you the probability of where this electron can be in this volume of space. So when you have this spherical shape, you refer to that as s orbital. Okay, so this this red positive sign is your nucleus, showing that there are protons inside it, positive, and then electron can be anywhere where you see this red dot, and because it looks spherical in shape, it's called s orbital. Then we have another possibility for the shape, which looks like this dumbbell. So you have something in the center, and then you have these two dumbbell shaped things, and that's referred to as a p orbital. And then there can be distinctive shapes that can come out of combining these orbitals, or the way they are oriented around the axis. So this is my spherical shape, so s orbital. These three are basically the p orbital, right? Because p orbital can be dumbbell shaped. So you have px, py, or pz, because you can have like x, y, and z. Sorry, this line is supposed to be passing through the, let me erase it. So x-axis, y-axis, x, y, and then z. So depending on where it is oriented, it is called as px, py, pz, but you don't have to know too many details of it because we are just doing intro to the chemistry class. However, know that there is one s orbital and there are 3 p orbitals, and the 4 orbitals centered on a single nucleus, which is the spherical shape. The spherical s orbital is shown only in the outline, okay, and the others can be seen clearly. So there's the blue one, the yellow one, and the green one, px, py, pz. Okay, so here's the slide that I've created, and I feel this works good for students. So we have s orbital or s subshell that can have a maximum of 1 orbital, and that can hold, we know that if n is equal to 1, it can hold maximum of 2 electrons. So that's why s can always have 2 electrons, and we write electrons on top of the orbital. So we write s square, that means that is telling you that it is s orbital and it has 2 electrons. Like that, you have p orbital and it can have a p subshell, and it has 3 orbitals. So orbitals are usually shown like a box here. So s will have only 1 orbital, p can have 3, as we just saw, px, py, and pz, and then each orbital or each square can hold a maximum of 2 electrons. So if the electrons are shown as these arrows, they're always in the anti-spin. So one spin is going up and one is going down. So this p, because each can accommodate 2, you can have a maximum of 1, 2, 3, 4, 5, 6 orbitals. And we don't only have s and p, we have more subshells like d, f. D can have 5 orbitals, and whenever you have 5 times 2 is 10 electrons. F subshell has 7 orbitals, and 7 times 2 will give you 14 electrons. So that's how you need to know. So let's look how can we actually now arrange these electrons, and this arrangement of electrons is referred to as electron arrangement. So whenever you'll see a term called as electron configuration, so that is going to allow us to represent this arrangement of electrons in an atom. So in the example shown here, you see 1s square, where 1 is telling you the electrons are in the first shell. S is telling you that the electrons are in the s subshell, and 2, as I told you before, is telling you there are 2 electrons in 1s subshell. So let's look at an example of nitrogen. Nitrogen, if you look at the periodic table, it has atomic number of 7. That means it has 7 electrons. And if anyone is wondering how does she know it's 7 electrons, because by now you should have practiced what we learned in the earlier part. So atomic number is the number of protons, right? And because nitrogen here is neutral, so the number of protons are equal to the number of electrons, and that's how we know we have 7 electrons. So anyways, so the nitrogen has 7 electrons. So we will start with 1, and the first orbital is s, and we can have a maximum of 2 electrons in s. Now 1s is filled. Now I move to the second main shell, which is 2 my subshell, first subshell is S. It can have a maximum of 2 electrons. Then after S comes the P subshell. So I write 2P, and P can have 6 electrons. But let me count my number of electrons. There are only 7 electrons for nitrogen, and I've already used 4 out of 7. So there are 3 more electrons left, and I'm going to write 3. And then I'm going to count 2, 4, 5, 6, 7. So my 7 electrons are shown here in this electron configuration or electron arrangement. So need to practice this because there will be questions on that. And if you wonder how do I know this order of filling, is because you have something, a chart like this, which tells you the orbit, how these electrons get filled. So see this, 1s gets filled first, follow the arrow. After 1s comes 2s, follow the arrow. After 2s comes 2p, keep following, 3s, 3p, 4s, and then something changes. After 4s, there is 3d, and then there is 4p, 5s, and after 5s comes 4d, and then 5p, 6s, and then the f orbitals come into place. So 4f, 5d, 6p, 7s. So you need to know this arrangement. It's a good idea to write these down in this order and then keep following the arrow. So that way, in the beginning, when you're practicing writing the electron configuration, you will not make a mistake. So you expected to know the electronic configuration for at least the first 20 elements. So I would recommend practicing these, and if you write each one of these, you will get a hang of it, and then it will look easier. Okay, so if you don't have this table, which you will not have in the exam, so without referring to this table, use the subshell notation to write the electron configuration for oxygen and sulfur. So I'm going to show you one here, and the first thing would be oxygen is represented as O. You will look at the periodic table. It has an atomic number of 8. So oxygen is, let me just erase it because I have a few more things coming up. Okay, so oxygen is, atomic number is 8. So what are the steps? So it has 8 electrons. So we will start with the shells, subshells, and we will start with the lowest energy level, right? So oxygen 8. So I will start with 1s, and s has a maximum of 2 electrons. Then I go to 2s, 2 more electrons, and I go to 2p, and then I actually count 2, 4, and I have 8. So 8 minus 4, so I will write here 4 because I can have maximum of 6. So that would be my electron configuration for oxygen, and you can practice that for sulfur, which has 16 electrons. So sulfur, I would pause the video here, write the electronic configuration for sulfur, and then I can check the answer. So the last part of the chapter involves actually the periodic table. So let me quickly get on to that. So far you have seen a periodic table, right? Everyone has seen a periodic table in their chemistry book. So basically it's considered to be a predictive tool for everyone using the chemistry. It is made up of vertical columns, which are called groups, and earlier it was referred to as families. And then you have horizontal rows, which are referred to as periods. So let's see. These groups or families, uh, they are the vertical columns, as I just said, and they contain elements with the similar chemical property. So that's important. That's how they are organized. And periods, the horizontal rows, so each element in the period demonstrate a range of properties depending on what elements are metals, what are non-metals, what are metalloids. So let me show you a periodic table and get on to these terms. So here's a picture of periodic table, and look here, period number. So you have basically 1, 2, 3, 4, 5, 6, 7 rows here. And then you have your groups, and your groups can go from group 1A, 2A, or they can also be called as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you see there are basically 18 columns which are referred to as groups. And earlier they were also subdivided as A and B depending on where in the periodic table you put them. So there are 7 horizontal rows and there are 18 columns which are referred to as a group. And then you see these 2 rows which are at the end. They basically were discovered later, so they fit in here, and this first row is called lanthanide because it's after the element lanthanum. So these elements, see, lanthanum was 57 and the next element here is 58. So this row actually goes in here, 71, and then 72 starts here. And the second row is after actinium, and that's why it's called actinide. So lanthanides and actinides. You see like how you have group 1A, group 2A, and then it jumps all these groups in here, and then it says group 3A, 4A, 5A, 6A, 7A, and 8A. And these elements which are fitted in here are 3B, 4B, and so on. So these B elements were also discovered slowly, so that's how they are fitted in here. And that's why they are referred to as B group, group 1A, 2A, or you can just refer to as group 1, 2, 3, 4, 5, 6, 7, and 18. I'll go up to 18. Another term which is very important in electron configuration and also the way the elements are in the periodic table is the valence electron. So valence electrons are the electrons in the outermost principal energy level of the electrons. So the electrons which are in the outermost level. And these electrons, because they are in the outermost level, it's easy to gain or it is easy to lose them or share them in a chemical reaction. So the elements in a group or family have the same number of valence electrons. So what do I mean by that? So when I showed you, this is like they have split the periodic table in different groups. So here you see group 1A and 2A, and here group 1A has all the elements with the similar properties and they're called alkali metals here. Group 2A, they have all the elements in having the similar properties and they're called alkaline earth metals. Then you have these inner transition metals which were the lanthanides and actinides, and then you have transition metals which were all these B groups. And towards the right hand side of the periodic table you continue with this 3A, 4A, 5A, 6A, 7A, and 8A. And then the group 7A here are called halogens, and group 8A are referred to as the noble gases or the inert gas elements, depending on their properties. So some groups in the periodic table, they have these specific names. So the 4 groups that you are expected to know are alkali metals, which is also referred to as a group 1A, and the valence electron configuration in this group is NS1. So N can keep changing. It can be 1, 2, 3, 4, 5, 6, 7. But this outer electron 1 is characteristic of this group. And that's why all the elements in this group will all have 1 valence electron. The alkaline earth metals is referred to as a group 2A. And as the name suggests, 2, they have 2 electrons in their valence electron they have 2 valence electron in their outer shell. Halogens, which is group 7A, they have 7 electrons in their outer principal shell, so 5, 6, 7. And the noble gases, they're referred to as group 8A, and this is their configuration, 6, 7, 8, so 8 electrons. And now I'm going to quickly tell you about each group. So here is your first group, the alkali metals, group 1A, also represented as NS1. So these elements, lithium, sodium, potassium, rubidium, cesium, they all are in group 1 element. And if you look at their atomic number, so lithium has an atomic number of 3, and if we have to arrange them in their electronic configuration, which we did before as well, so 1s2 and 2s1. So this is their valence electron. So they have 1 valence electron, ns1, outermost principal level. Similarly, sodium would be 11 electrons, so it will be 1s2, 2s2, 2p6, and 3s1. So similarly, you can see that all of them have that ns1 configuration. And here, lithium is the least reactive. Sodium, potassium, rubidium, cesium, they are more reactive. And here are these elements shown. Lithium is the hardest metal in the group. And sodium is a soft metal, and so on. The properties depend. You are not expected to know the properties, but you definitely need to know what is alkali metals. So you should know it's a group 1A. What is its electronic configuration? NS1. And if I ask you write the electronic configuration, then you should be able to write it looking at the atomic number from the periodic table. Hydrogen is the odd one in here, which sits on top of lithium. It's not an alkali metal, rather it's a typical non-metal. So these are showing you how vigorously they react in water. So here is lithium, you can see the bubbling, and then here's the potassium, and you can actually see it catching fire. And sodium will also catch fire. Next group is your alkaline earth metal group with a configuration of Ns2. These are mostly soft metals. They're moderately reactive. Beryllium is the one that's hard, and then magnesium, calcium, strontium, barium, and radium are progressively more reactive towards water. And the third group that we talked about is halogens, group 7A, Ns2 and P5. Here are the halogens: fluorine, chlorine, bromine, iodine, and this is how they are all diatomic. That means 2 atoms. So Cl2 gas, Br2, I2. Out of these, fluorine is the most reactive. Fluorine and chlorine are gases at room temperature. Bromine is actually a liquid, and iodine, as you all know, is a solid. The noble gases, which is the last group of elements in the periodic table, they are referred to as group 8A or group 18, and they're represented as Ns2Np6. And if you see, they have a complete set of valence electrons. So they have 8 electrons in their outermost shell. So that's the reason they don't want to share the electrons. They do not want to give away their electrons. They are happy the way they are, and that's why they are also called as inert gases. They undergo rare chemical reactions. They have very less chemical reactivity. So here is a slide which talks about the valence shell electron configuration for phosphorus and strontium. And it's asking you the valence shell, so you're just required to write the outermost electron configuration. So let's try the phosphorus. You will look at the periodic table, and as you see the periodic table, you will see it's a group 5A element. That means it will have 5 valence shell electrons, and then you will look at what row is it in. So it is in third period, so its electronic configuration will be 3s2 3p3. So what I mean by that is you will need to see a periodic table here. And similarly practice for strontium. So strontium, as I showed you, is in group 2A. So what is the configuration for group 2A? It is NS2, and you know that because it's an alkaline earth metal. So then you will look at what period is it in. So it's in the 5th period or the 5th row of the periodic table. So you will just put N is equal to 5s2. Okay, the last point here is where are the metals, where are the non-metals and metalloids in the periodic table, and what are they? And you will study more in the lab about it. So metals, they are classified with the nice metallic luster. They are good conductors of heat and electricity. They are malleable and ductile. That means they can be flattened or they can be made into wires. So for example, a copper, you all know, is a metal. It has a certain metallic luster. You all have seen copper metal. You can either have flat copper sheets or you can have copper wires. So that's what you mean by malleable and ductile. Metals are on the left hand side of the periodic table. Non-metals, as it says non, so they don't have a bright luster, so they are dull. They are non-conductors and they are brittle in the solid state. And examples are sulfur and bromine. And metalloids are somewhere sitting between the metals and the non-metals. So they have the properties of both metals and non-metals. And a classic example is silicon and arsenic. So here are the few slides where you see metals such as gold, and here is a non-metal such as sulfur, which is brittle, melt at low temperature, often a good insulator. And gold, you all know, it's a precious metal. People like to use it in ornaments. It can be easily shaped. It can conduct heat and electricity. And then your chapter concludes with this green chemistry examples, where the first example is given for the solar fuels, like how sunlight, as we know, is a great source of energy, right? It's abundant source of energy. And if you have taken a chemistry class, you have seen this example, how these plants store solar energy and then they convert it into a chemical energy by a process called as photosynthesis, right? So carbon dioxide, water, and sunlight forms carbohydrate and oxygen. So that's the natural chemistry, and then people can create this artificial photosynthesis reaction to generate hydrogen fuel. So first is the photosynthesis reaction that I showed you 1 minute ago. I just put it together for you to compare. So in the artificial photosynthesis, you will have water split into hydrogen and oxygen. So H2O is split into, used as a hydrogen fuel, and O2, and then they balance the reaction. So basically you put 2 here, that's the balanced reaction. Okay, and so this hydrogen fuel, which I just showed you, can be reacted with oxygen to produce heat and electricity. So the water use the solar energy in the solar cells, create this hydrogen and oxygen, which can further produce heat or electricity. So that wraps up the chapter. My advice for you is use create or draw a periodic table for yourself and fill up these blanks like group 1A or group 2A, and then what are these groups called, where is your noble gases. So group 8A, halogens, group 7A, what are these called, alkali metals, alkaline earth metals, noble gases, halogens, transition elements. This side is metals, here are the non-metals, and then the zigzag line is the metalloids. So I would advise you to know these and practice these well. Thank you.